All right, so here in this video, we want to talk about a relation. So we briefly touched on it earlier in the course. So what is a relation? Is a relation just in general is where we have some kind of ordered pairs between a set, sometimes two sets, but it could be within a set itself, right? So it's a binary relation. It's a set of ordered pairs. We say the binary relation is a relation that it's A and B, provided the ordered pairs are a subset of A times B. We say a binary relation is a relation on a set A, provided the ordered pairs are a subset of A cross A. So a relation is what we call some kind of Cartesian product. So what that means here is when we talk about relations, here we're talking about some set of ordered pairs. So the order of the elements is going to be important. So here, right, so here, so this is what's known as a Cartesian product. So A cross B, where we have an ordered pair AB, right, such that A is an element of A and B is an element of B. And sometimes they are a subset of, sometimes we'll have of the same set, right? Sometimes we'll have A cross A. Right, now sometimes these relations can be written as graphs, right? But graphs really represent symmetric and irreflexive relationships, right? So, but our relations sometimes are going to be, well, they won't be symmetric, and sometimes they'll be reflexive, where an element can be kind of mapped onto itself, right? Or self loops, right? And we'll look at the two examples here. We'll go over two examples in our textbook here to see what I mean by reflexive and right, and also directed, right? So when we talk about a binary relation, right, we're talking about two sets like this Cartesian product here, right? A and B. A relation on a set A is a subset of A cross A. A graph's edge set is symmetric, an irreflexive relation on its vertex set. So graphs are really what we're saying here is graphs are a special case of these relations. Right now, and sometimes we can write these relations as graphs, the simple graphs that we're used to. Sometimes we can't. Right, so let's look at, this is example 2.6.3 in our textbook here. So that example states here that so we have two sets of students, or excuse me, a set of students and a set of classes. Right, so A is the students, Al, Bob, Kat, Dirk, and Eva. All right, and the set B are the courses, and the courses in question are calculus, discrete math, and stats. Okay, and we are told that everyone except Dirk is taking calculus. And then Bob and Eva are in discrete. And Al, Kat, and Dirk are in stats. Okay. All right, so that's the setup. And here what we're gonna do is we're gonna define a set, a relation, excuse me. We define a relation T, and the relation is taking, right? And then we can write these, that holds a student and a class, all right? So student is taking class. All right, now to define the relation, right? So it's binary in the sense that one element from each set, right? The set A cross B, right? So T is going to be defined by the student Al, and we can see Al is in calc, and he's also in stats. All right, and then we move over to Bob. So Bob is in calc, and also Bob is in discrete. All right, and then we have Cat. Cat is in calc. Right. Again, everyone except Dirk, and Cat is also in stats. All right, and then Dirk is in stats. And then lastly, we have Eva, who is in calc. And Eva is in discrete. Okay. All right, so that is our set here. And then the question is, can I write this as a graph? And it looks like I have two right, distinct sets. This is going to be a bipartite graph, right? We can have L. One of the sets is the students, Bob, Cat, Dirk, and then Eva. And then my other set being the classes, calc, discrete, and stats. Okay, so here looking at our relation up top, Al is in calc and in stats. All right, Bob is in calculus, and he is also in discrete. And then Kat is in calculus, and she is also in statistics. And Dirk is in statistics. And then Eva is in calculus, and she is also in discrete. Okay. Okay. So that is how we have a relation, right, that I can draw as a graph. Now let's take a look at another one that is not a graph like we have seen in this course to this point. So we want to consider the relation M or is a multiple of. All right, so it's across one set made up of the numbers 1 through 6. All right, so I'm going to start by writing the ordered pairs. So M would be defined as, right, so starting here, 1 is a multiple of 1. And that's the only one, right? So now, let's say 2 is a multiple of 1, but 2 is also a multiple of itself, 2. And then 3 is a multiple of 1, and 3 is a multiple of 3. 4 is a multiple of 1, 4 is a multiple of 2, and 4 is a multiple of itself. All right, and here 5 is a multiple of 1, 5 is a multiple of itself. And then lastly here, 6 is a multiple of 1, 6 is a multiple of 2, 6 is a multiple of 3, and 6 is a multiple of itself 6. All right, now this is not a graph in the sense here, it's not symmetric, right? So before the order would not matter for our simple graphs here. So we notice that we see the outer pair 6, 2, but 2, 6 is not in there. Right, so it'll be different in that sense, and also previous graphs we did not allow edges between a vertex and between itself, right, within the same vertex. So what we have here is what's going to be a directed multigraph, right, where the direction is going to matter, and we're going to allow loops, right, so it'll be reflexive, right, and the direction is going to matter here, right, so our graph would look something like this: 2, 3, 4, 5, 6. All right, now each one of these is reflective, so in a sense we have this kind of loop. Right, where it loops onto itself. All right. And now the direction 2 is a multiple of 1. So that looks, so moving along, right? We got the 1, 1. That one was taken care of by that self loop. And 2 is a multiple of itself. So already the self loop there. Then moving on to 3. 3 is a multiple of 1. Right? So it goes in that direction and of itself. So it loops back around itself. Now 4, multiple of 1. 4 is a multiple of 2. So we have another. Again, order matters here, directed arrow there. And 4 is a multiple of itself, so we have that loop there. And then 5, a multiple of 1 and of itself. And then 6 here is a multiple of 1, multiple of 2, multiple of 3, and multiple of itself. All right, so here we have a directed multigraph. Okay. All right, so there's just a couple of basic relations here. All right. We also have this idea of inverse, right? So we can define an inverse relation here. So our inverse, right, is going to be the relation defined here. It's an ordered pairs BA, right, such that AB is in R. All right, so that is the inverse. And we can also have a composition, right? So just introducing the composition where we have two relations, right, on the set A, B, and C. Right, so we have is a composition where we have AC. Right, that's an element from A cross C, and then AB, element of R, and BC, element of S, for some B in B. Okay, so you can see, right, there are some similar type operations that were used, have seen before with functions, right? But now here we're looking at discrete relations.